Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. The engineer in the Signature Modeling Group and has been involved in a variety of thermal and EO/IR efforts during his tenure. Notably, he has aided in developing processes to create high-fidelity synthetic terrains using real-world inputs for scene simulation and investigated synthetically trained AI/ML version algorithms for automatic target recognition. He has been with Thermal Analytics for over 2 years and received a BS in Mechanical Engineering from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation along with the slides. And with that, Alex, if you're ready, you may begin.
All right, hi everybody. I'm Alex Calasius, and today I'd like to talk about MuSES's electro-optical infrared capabilities for artificial intelligence and machine learning applications. First, I'll give a short AI/ML introduction. We'll introduce MuSES, our flagship EO/IR software package, discuss how Thermal Analytics can create synthetic scene terrains, go over how you can create image data sets with our process automation tool CoTherm, and then show some internal working examples and some of the progress our customers have made using our tools. AI and machine learning have become very popular areas of research in the past few years, and that is expected to grow more prevalent every year. Precedence Research, a marketing research organization, recently released a report which estimates that the AI/ML market, specifically within defense, is expected to grow 2.6 times within the next decade, from about 8 billion in 2022 to around 23 billion in 2032. With previous machine learning algorithms showing high performance in tasks such as target detection and recognition, and this estimated growth over the next decade, it will become increasingly important to make sure that the information that's being used to train these tools is of a high quality. We know that these sorts of deep learning approaches can perform complex image processing tasks without explicit instructions or manual feature extraction, but they require a large set of training images on which to base their statistical predictions. These data sets in the visible spectrum are relatively easy to come by, but it can be very difficult to find data sets large enough and with enough variability to train outside of the visible spectrum. In this case, we're going to talk about the infrared, from the near IR to the long wave IR. So the acquisition of suitable image data sets can be a limiting factor for how these deep learning approaches are used. But infrared scene simulation can be a viable alternative to measured image data sets. But Thermal Analytics has a history of scene simulation and can help you if your desired imagery can't easily be found, capturing your own imagery is too resource intensive, or if you aren't able to obtain your desired targets, possibly because they're either foreign made or they're adversarial targets. Throughout TAI's history, we've developed an extensive model database. This includes tracked and wheeled ground vehicles of different uses, airborne targets including jet aircraft, helicopters, and drones, maritime targets of multiple sizes, and personnel in numerous poses. We can use these target models to help fill any potential gaps in IR imagery by using MuSES, our flagship EO/IR software. MuSES is a thermal solver and an EO/IR rendering tool, which takes inputs such as 3D CAD geometry descriptions, part material thicknesses, and thermal properties, as well as component heat sources and boundary conditions such as sun location, the sky background for radiation exchange, and air temperature and speed for convective heat transfer to properly set up the analysis environment. Once these are combined, we can get a physical temperature prediction of the target. Sensor images can also be generated, which can either be specular or diffuse, as well as spectral or across a broad band of wavelengths. And we can also get contrast metrics, such as delta TRSS and contrast radiance. Being able to gather all this information from one software is what helps make MuSES such a powerful tool for those who care about the IR spectrum. However, there is more that MuSES can do. MuSES can model exhaust plumes for added signature accuracy. Oftentimes, these plumes can be hotter and or larger than the hard body target, so ignoring it could underestimate the overall signature. To do this, MuSES imports a volumetric CFD result from an external analysis tool, such as star CCM, and will calculate plume radiance when creating rendered images of the target. This plume radiance is only calculated for ray tracing paths between the scene and the sensor, which pass through the area of the imported CFD result. We also support the inclusion of CO2, H2O, and carbon soot as species within the plume. MuSES can also model human targets in the IR spectrum. In order to do this, Thermal Analytics has developed an accurate human thermal regulatory model, which incorporates metabolic heating, shivering, respiration and sweating, vasomotion, in order to accurately predict tissue and core temperatures. Laser illumination is another capability of MuSES. Hard body and component heating from a directed energy source can be included in the thermal simulation, and users can specify laser parameters to include a narrowband source in their sensor renderings. We can also handle IR simulations of satellites for various orbiting payloads and sensor platforms. This can include electrical thermal simulations of battery systems, solar panels, internal electronics, as well as passive and active thermal control systems. MuSES also offers some flexibility on the amount of detail used in a ground scene simulation for both the target and the background. We can use a default background option in the software, which automatically will create an infinitely large ground plane underneath the target. A faceted background can also be implemented, where we assign physical surface elements as part of the background and use geometry to represent different types of discrete clutter. A higher fidelity textured background can be another option, where we use satellite imagery to create a ground truth representation of the target. We can also create composite imagery, where we simulate the target in MuSES and then insert it into a measured background that's been radiometrically calibrated. And we're partnering with other software companies such as Dursig and Octal to allow you to insert our target models into their scene simulations. The textured terrain approach that I discussed on the last slide is something that TAI has been investigating and developing in recent years, and I'd like to discuss it further with you. TAI has developed an in-house process to create realistic-looking textured backgrounds via open source information such as satellite imagery and digital elevation maps. Here we can see one such example background. On the left, we have a satellite and topological representation of the target area, which is drawn inside of that yellow box. And on the right, we have the terrain scene in MuSES after it has gone through our textured terrain creation process. This process captures topological relief and on an element basis automatically separates different types of ground cover, such as bushes, trees, gravel, dirt, sand, etc., which are represented by different colors in the model. Due to the open source information that is fed into this process, it can be used for almost any location. And TAI is actively researching and expanding this process and its capabilities. Here we can see a few sample images using this background creation process. These images are in the mid-wave infrared and the long-wave infrared and are simulated at multiple points throughout the day. The difference in color throughout the background is due to a computationally efficient way to model background clutter and variation without needing to use a large number of surface elements to explicitly model clutter objects in the scene. In addition to the previously shown background, we have numerous terrain possibilities within our database that range from the urban to the rural and from deserts to mountains. As you've seen, a lot of different information goes into making a target model, and adjusting all of the parameters manually to create an image data set can be very tedious. However, we can automate some of that with another TAI developed software, CoTherm. Inside of each target model, we have the geometry of the target from our existing database, optical surface descriptions, and terrain descriptions. These models are fed into MuSES with weather data and sensor parameters. After our analysis, synthetic images of the scene is generated, which can be fed into an algorithm to give some sort of deep learning output. To generate these types of data sets, CoTherm is our tool of choice. CoTherm is a co-simulation and process automation tool that's often used for complex multi-physics simulations that require coupling multiple software packages together, but it can also be used to automate a repetitive process and parameter variation, such as MuSES thermal and IR predictions over a wide range of environmental conditions. The CoTherm user interface is shown here. There's a process flowchart made up of a series of simple tasks that run to completion, so we're able to provide a graphical-based path for generating these large IR data sets of interest in an efficient manner. And we can quickly run through one such example of how we generate these data sets. So here we have an example thermal model that we could feed into our data set generation process. This is a Type 052A frigate for which we've spent time generating a high-fidelity geometry representation and have accurately parted out the geometry description based on different boundary conditions of the craft. And we've included a few heat sources, such as solar loading and internal engine heating. We can then analyze this thermal model and render it under numerous conditions. Here we've analyzed the target while it was off, while it was idling but not moving, and exercising through the water at numerous points throughout the day, in the open ocean and in a littoral environment, and created over 2,500 simulated long-wave infrared images for our desired sensor. A handful of the images from this data set are shown along the bottom. You can see it idling in open ocean. You can see it moving with a wake through the open ocean, and you can see on the right side it silhouetted against a littoral environment. By combining MuSES and CoTherm, we're able to efficiently generate large, highly accurate, and automatically labeled data sets, which can be used for training and testing various AI ML tools, such as those for target recognition. These data sets can encompass humans, ground vehicles, aircraft, UAVs, and maritime targets. Within thermal analytics, we have numerous projects that can highlight the capabilities of MuSES in the IR spectrum. One such project focused on human detection in multiple terrains, including urban areas, deserts, and woodlands. We generated synthetic IR image data sets using both CoTherm and MuSES, which we then used to train an object detection algorithm. And these data sets included multiple terrains, ranges, and times of day. Here we can see some example images of the terrains that were used in these data sets. This included a desert village, a college campus, a woodland, and an office park. The detection algorithm was trained on and tested with only these synthetic data sets that we created. When we look at the results of our testing, we can see some positive results. In this example image that I've shown here, we have two humans. If you can see them, I'll give you a little time to try and find the two targets. They're shown here by these yellow annotations, which tells us that our object detection algorithm found them successfully. And these yellow annotations show the confidence that the algorithm has in its detection on a scale from 0 to 1. This example image, along with our other testing images, gave us confidence to dive further into testing what limits this trained algorithm might have. We wanted to test partial occlusion, so we created some rendering images where the human targets were not fully visible, showing only the upper or lower half or the right or the left half. And when we tested these images, we were able to see success in the algorithm's detection of these targets. We then extended our testing to include measured imagery. We trained exclusively with synthetic data, which I've shown before, and then we generated and tested a measured data set scene. Here I've shown a visible image representation on the top and the IR video representation along the bottom. We observed many positive detections and good tracking of the targets throughout the entire IR scene. TAI plans to conduct more training and testing to improve the performance of this algorithm. One other project that we have done focused on automatic target recognition and how sensitive these ATR algorithms are to multiple variables in their training data when testing against measured IR images. To investigate this, we created multiple simulated IR data sets, which encompassed many changing parameters such as target to sensor ranges, view angle, time of day, weather conditions, and vehicle state, such as off, idle, or exercise. If you'd like more information, we've published an SPIE proceedings paper on this, and I can discuss it more after the webinar. But to accomplish this task, we also needed to find a set of measured IR images that we could use for our trained algorithm. The measured data set that we chose to use for this investigation is the DSIAC ATR dataset, which is publicly available. We used 6 of the 10 target vehicles, all of which were already in our thermal model database. We did not have a matching model for the pickup, the SUV, and the MTLB towing and artillery piece in our dataset, or in our model database, excuse me. And the T62, which was used in the DSIAC dataset, broke down during collection, and we felt it did not have enough viable information. We can qualitatively compare the measured images from the DSIAC dataset and our synthetic target models. All the images shown here were taken or generated at nighttime in the midwave infrared from 1,000 meters away. We can see a very good agreement between the measured images and our predictions. And to do this sensitivity analysis, we used an AlexNet neural network architecture, which we trained with strictly synthetic data and tested against only measured data. After investigating all of our imagery variable combinations, we found recognition rates up to 3.4 times better than random chance, depending on the variable combinations we used. And these results are shown in the heat map on the left, where the recognition rate percentage is visible, as well as a dark to light gradient for quick identification of highly performing combinations. Some of these variables that we investigated included alternate backgrounds around the vehicle, as well as tone mapping, which yields differing levels of contrast to the training and testing images. TAI plans to conduct further work to increase the recognition rates and better understand the domain shift from the synthetic to measured data. While thermal analytics has made progress internally to highlight our capabilities within the AI/ML application world, so have our customers. One such customer is Vected Thermal Imaging from Germany. This joint work with Vected was presented last year at the Armed Forces Communications and Electronics Conference in Germany, and I'd like to thank them for allowing us to share this work today. Vected aimed to show how their thermal cameras could be used for target recognition and distance estimation by using a scale model of a main battle tank and a trained AI. Vected used a plastic scale model of a main battle tank with an enclosed heated environment shown in the background underneath the camouflage net to yield better contrast from the conference environment. They hooked up one of their thermal cameras to a laptop to help visualize what the camera was seeing. And in order to create this trained AI that Vected was after, we provided them with one of our synthetic image datasets. And they used it to train some form of artificial intelligence using only our synthetic imagery. This synthetic imagery constituted a desert-like scene with vegetation and vehicles in an off state with no internal heat sources, including a pickup truck and 4 military vehicles of different roles throughout multiple times of day in various view angles. This AI model was then adjusted and fed into a thermal camera. When they pointed this AI-powered camera at their model tank, it was able to recognize it with confidence and give an accurate range estimation. This range estimation was able to be gathered passively and without the need for a laser rangefinder. In addition to target recognition and range estimates, Vected was able to predict which pixels of the camera corresponded to different parts of the tank model, such as the wheels in green, the armor in blue, and the turret in red. Vected was then able to further validate their target recognition and range estimates up to ranges of 50 meters. And again, I'd like to thank Vected for allowing us to share some of their results. Throughout this webinar, we've seen that thermal analytics can model high-value targets on land, air, sea, or space across the infrared spectrum. Thermal analytics can generate large and varied image datasets of these targets, including synthetic backgrounds, which can be used for AI/ML applications. And our products have shown viability within the AI/ML workflows to substitute for measured imagery training datasets, both internally and by our customers. And with that, I would like to say thank you and open the floor up for any questions.
All right, thank you, Alex. Let's go ahead and take some questions here. What types of data does the CoTherm generation process create?
Great question. This CoTherm generation process can easily create visual images. It can create a target mask based on your renderings, and it can also create NumPy arrays for any further analysis that you might want to do.
Right. Do any of the products fall under ITAR restriction?
Yes. MuSES is an ITAR regulated software. However, CoTherm is not.
All right, thank you. How long does it take to generate image data sets?
It can vary depending on the files and scenes that you're looking to analyze and their complexity, but some previous data sets that we've generated of around 50,000 images took about 2.5 total days of computer time, which was split across multiple machines.
All right, thank you. Can you vary ocean dynamics like storm to hurricane, category 1 to 5, etc.?
Yes, we can vary the sea state. That is something that we very much allow. Approaching hurricane levels of variation, I'm not entirely sure. I'd have to get back to you on that, but we can very much change how the sea appears and interacts with the target.
All right. How long will it take to train these sorts of algorithms?
That again is quite variable, but if you have experience in it, it may only take a few days or weeks, depending on what you're trying to teach it and how much information you're feeding it. But if you're trying to learn along the way, and this is something you're still new to, it could take a month or two to see accurate results.
All right. Have you done any validation or repeatability studies on your machine learning models?
At the moment, that is something that we have on our priority list and are looking to do, and it's something that we'd very much like to investigate, but that isn't, or we do not have results that we are ready to share at the moment.
All right, thank you. Well, looks like that'll do it for questions. So that will complete today's webinar. Thank you, Alex, and thank you, everyone. We appreciate you all for attending. You will receive a follow-up email, slides, and watch the recorded webinar session. Again, thank you, everyone, and have a nice day.